All right. All right, so let me call up the lab manual here. Let's see, that would be 102 class. And let me load here. Well, that was a little slow. Hopefully that's not normal. Where is that lab manual? Lab manual right there. Okay, good. And then Spectra. Spectra looks like it's down on page 93. Okay, so let me roll down to 93. Good. Good. And maybe I'll go ahead and do a share screen. I don't know if we'll need it for these discussion ones, but it might be nice to see it in writing as I say the words. Let me start my Bluetooth here. And that should connect here. Well, that's finishing connecting. Let me come back to the lab. Oh, okay, and then here. All right, so here's the questions finally. All right, so let's run through these questions. The first one, I guess I'll call it number one here. They don't label them in this book for some reason, but it says, what difference, in any, did you observe between the sunlight and the incandescent bulb? Well, let me go ahead and say you can skip this one because we didn't do the sunlight in the class discussion or in the lecture, what am I trying to say? I guess it's the video lab. It was foggy that day and there was no sunlight we could do. So we skipped it. But however, I will just say in passing, because I think I said it there on the video, that the answer is you should be seeing the same. And so the same reason the incandescent bulb gives off light, because we're just, pumping energy and getting it hot, the sun does the same thing. And so that's really what they wanted you to notice, that it was a whole continuum of spectrum from the reds on one side to the violet on the other, and the sunlight was the same as the incandescent. That's why well, besides making that point, that's also why we have both of them, because we can never be guaranteed about sunlight on any given lab day. So we always have the full spectrum, whether we get it from the incandescent bulb in the lab itself or move on to the sunlight. Okay, so if I go to the second question, question says the red filter is an example of a narrow filter. What does this mean by narrow? And so if you look at the data sheet, what you were supposed to have drawn is on this side of the scale is the 400 nanometers light, and on this side of the scale is the 750 nanometers. And in the incandescent one, so the one right before this question, right before the red one, this thing would have been full. You would have, over on this side, you would have had your reds, then your oranges, your yellows, your greens, your blues, your indigo, and then finally your violet. And what they mean here by narrow is it just lets in a small piece, a narrow piece. And so you probably didn't see these. You may have seen a little bit of yellow. That one's kind of questionable, but you mostly saw the reds and the oranges. So the question says, what does it mean by narrow? It means it just gives a small piece of the whole spectrum. So small piece of whole spectrum might be a good way to just write it. That's what we mean by a narrowing of the filter. So you start with a lot of light and you narrow it down. Sometimes we call that an absorbing filtering. Okay, so now the combination of the cyan filter and the yellow filter illustrated color mixing by subtraction. Explain what happened. All right, so before I explain it, let's talk about this. Again, if you look at your spectrum from your 400 to your 750 for, let's see, let's do a cyan. Now, cyan's kind of a blue-green. Now, right on above it, why don't I write the spectrum again, the Roy G. Biv. And the cyan is kind of a blue-green. And so with the cyan there, you probably saw things like blue, green, maybe even a little bit of yellow. But it, too, is a narrowing filter. So you ended up blocking the two extremes of the spectrums, the red and the orange, and the indigos and the violets. And then the other one, the yellow filter, would have looked something maybe like this. You would have let in your yellow, that's why we call it a yellow filter. It would have also maybe let the adjacent colors through, which is maybe the orange and the green. So again, this is a narrowing filter also. It narrowed it down, blocked this edge of the spectrum and a lot on the other edge of the spectrum. But when you put the two together, so you start with all the colors, and then you narrowed or subtracted out all of them except the blue, the green, and probably most of the yellow. Maybe a hair gets through. Maybe I'll cross it out for a deeper discussion here. But then when you pass it through the next filter, you do more subtracting. That is, you would block out, the second filter would block out anything that's not in this part of the rainbow, which of course would be this blue. And so ultimately you get just the green, maybe a small amount of yellow. But for discussion reasons, I'll block that out because this is really what you saw after you went through both filters. You saw a very green light. You saw only green coming through. So to answer the question, it says the combination of the cyan filter and the yellow filter is an illustrator of color mixing by subtraction, and explain what happened. So I would just say that, you know, we started with a full spectrum, and then, let's see, how do I want to say, subtracted, and maybe list them separately. So you could say, and then subtracted, and then if here I would go subtracted indigo, violet, orange, and red first, then subtracted, and then what would have been left here would have been just this. You might even say yellow in this first one. So you really just have blue-green. That's why it's called the cyan filter. And like I said, it does a little bit of yellow. But then the second one, you subtracted the blue. And then therefore, only green is left. I suppose might be a way to explain what happened. But the idea of getting a final color by subtraction is here. In other words, you start off with all the colors and you subtract them. This is really no different than if you drive a car. You might know that brake lights are red. Some turn signals are amber. I'll just go with the red. But if you were to look at the light bulb is actually a full spectrum light bulb. It gives off all the colors, and then you put a filter in front of it that only lets the red through. You subtract off the other one. So that's kind of what this is after here in this first three questions. Now, if we continue down here, the next question, I guess we're on question 4.
Yeah.
1, 2, 3, 4. Yeah, there's only 5 here. is number 4 says the line spectrum occurred with low pressure gases and a continuous spectrum occurred with solids. Why is this? Yeah, this is a tough one to kind of understand. Let me do this, that the incandescent filament, which is made out of a tungsten, but I'm not worrying about the material itself, when you get it really hot, and of course we got it hot by passing electricity through it, so we put an electrical current through there. But again, not worrying about how we got it hot, because the same thing happens in a fire and welding and all kinds of other things that are hot. The atoms then move around. They bump around faster and faster. And this is the physics we learned back in, I think that was chapter 11 of this class, where we said, what's the difference between something hot and something cold? And something hot, they're ricocheting around. And what ends up happening, though, is there's kind of 2 movements going on in here. There's the actual movement of the atom itself. So the atom moves, hits another atom, bounces around. And so that's kind of a movement going on, a shaking going on, if you will. And that produces light. And that would produce light at the frequency that it is shaking. Now, because there are so many atoms, sometimes it goes a short distance and sometimes it goes a long distance. And so the rate at which it shakes depends upon the rate at which it hits it. So in a highly pressurized gas or in a solid where, I don't know if I'd call it high pressure, but they're right next to each other, you get the whole spectrum. And so we saw the whole spectrum, Roy G. Biv, when we were working with the light given off by either solids or high pressure. And again, the reason why is because as they move along, some of them will take a long distance before they hit, so they will have this long wavelength. Others of them will be ricocheting off of each other in a close proximity, so they will make a short one. So these are the ones that make the indigo and the violet, and these are the ones that make the red. And of course, we have the stuff in between, and we have everything. And so the incandescent bulb, coming from a solid, gave us all the colors. However, if you then take a gas, and so you get the molecules far apart, that's why it will only work with the gases. Uh-oh, my camera froze. Okay, let me reconnect that. Share my camera.
It's black? Oh, yes.
Pardon me?
I mean, I can see the camera.
Oh, okay. There we go. Got the camera now?
Yes.
All right. Good. Okay, so what I was trying to illustrate, maybe taking too long to get there, is that when atoms are close together, they bump into each other at a whole variety of rates. High frequencies, low frequencies, and so they give off all the colors because the color is frequencies based upon the movement of those atoms. When you go to a low pressure gas, and the lower the pressure, the better, and the idea is the atom itself will actually move and never hit another molecule. The first thing it's going to hit is the sidewall. Now, you can't do that perfectly. You don't have much control on it, but the lower you make the pressure, the better this works. And when something like that happens, then the light is given off. And so let me look at the atom itself. The atom has a nucleus and an electron that is going around. And so there's our movement. And this movement of this electron is what gives off the light. And this is a well-defined movement unless it collides in with something. And therefore, if you look at our low pressure experiments, I'll just pick on sodium, for example, because the sodium light only released light in this kind of narrow range here. All you saw was this yellow. It was at about 590 on the scale. And the reason the sodium only gave off that light was because it is this frequency that this electron is going around. And so that's the only rate it gives off. The only way it can give off other frequencies is if its motion were to collide, and that you would get that when you put it in a high pressure. So high pressure sodium would give off a lot more set of colors, whereas the low pressure only gives off one set. Now, if we pick on another gas, how about mercury was another one we did. There were 3 different colors. And that's because there is usually more than one electron in the atom doing its thing. So you get a set of colors that is kind of unique for that particular element. So that's kind of nice. You can tell what element you have by what color is given off. And this, by the way, is the lead into the last question. But you don't get a whole continuous spectrum because you only have the motion of those electrons, which is unique for that element. And so I guess to answer the question, let's see, let me read it carefully here. It says the line spectrum, so this is called a line spectrum. So a line spectrum occurred with the low pressure gases and a continuous spectrum occurred from the solids. Why is this? And I guess I would say, to make it simple, that the solids had more collisions well, not writing a whole paragraph. I'll just say more collisions because the atoms are closer. How about that? Together. That might not be a bad way of kind of saying that in a short phrase of what I'm trying to say. So when they're close together, they bump into each other at all kinds of random frequencies, and so that frequency is the color, and so you get all the different colors. But at the low pressure, they don't bump into each other. You only have the frequency that's the internal frequency of the atom itself, and that's a unique one to that own atom. And so you only get certain lines. You get a red, a green, or a blue, or something like that. Which then gets me to the 5th question here. It says then, what caused the strong green line in the fluorescent spectrum? And so again, if you kind of look at your experiment before the fluorescent, let me just scroll up, because I think right before the fluorescent, you did mercury, yeah. And in the mercury, I'm trying to go by memory, Roy G. Biv, but that mercury, you should have seen 3. You should have seen a really bright green one, so somewhere around here. You should have seen kind of a blue indigo here. And I believe it's kind of a reddish orange there. That's the one I'm not 100% sure from memory what it looks like. But these 3 colors are what I was trying to say a moment ago, that if you look at the movement of the electrons inside of Mercury, they are going around at a rate that corresponds to the frequency of these three. That's why when you have a low pressure Mercury, you only see these three colors. Oh, you know what? Maybe it was closer to the yellow than the red. Yeah, I think it was. So forget that one. But the one I'm focusing the question on here, it is this green one, because then when you looked at fluorescence, you saw this identical green one. Now you saw some other things in the fluorescence, but here's the point of number 5, is number 5 is to get you to realize that this green one exactly matches up with the Mercury. And so you are supposed to be saying here that, let's see, what cause of green? You would say Mercury is in the fluorescent tube, because that just stands out. If you look closely, you'll see kind of the other two also in that fluorescent one. But you'll also see other things inside of that fluorescent one. So that tells me that Mercury is in there, but it's not the only thing in there. So that's what that last question was trying to get at. All right. Did that help?
Yes.
Good. And I'm really glad we started with a 102 one, because I know that you guys wait around for a long time, because some of these 122 questions are really long and challenging.
Yes.
In fact, didn't you ask something? Page 90. Oh, you're helping me out. Thank you. I was gonna say, because if you had another one on 102, I'd answer it now. So I need to scan and ask you if you got another one from 102, or if anybody else does. Let's see, 122. Jake, I believe a small error in the solution. Okay, but that's 122. Okay. All right. Well, we're good with the 102 here. Let's jump ships here and go to the 122. All right. So Anthony, you're next here. Can we do, let's see, exam 3? Sure. Number 5, sure. I think exam 3 though had 2 number 5s, didn't it?
Yeah, but they're both like the same problem.
Oh,
pretty much. So I just need one of them, and then I can do the other by myself.
Okay, so okay, let me just call it up here, and let's see, what did I do with the so the practice test would have been on the solution page. Okay, here we go. And oh, I see, number 5. This is the AM broadcast, and if it helps, don't get me wrong, I'll do it. But yeah, I see what you're saying. They're nearly identical. And then it's also, I did it right at the very, 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 very end of the lecture. If that helps, the one I made last Tuesday, I was starting to talk about energy, and I realized I'd been talking for a long time, and then I stopped, and so I didn't get into momentum. But anyways, let me just write down the time. It is 10:27, and I will then give this one a shot here. All right, so exam 3, number 5, and it says this. It says an AM radio station broadcast isentropically, which means equal in all directions. Oh, good, and it defines that word for you. With an average power of 4 kilowatts. Well, what is the voltage produced in a metal rod that's an antenna that is 65 centimeters long and it is 8 kilometers from the transmitter? Okay, so let me start with the idea of the intensity. The intensity is defined as the power per area. And so if you've got this like radio transmitter, so here's the transmitting tower, and it sends out these, in this case, radio waves. But hopefully what you guys got out of this chapter is there's a whole electromagnetic spectrum. And so whether they're radio waves or whether they're microwaves or whether they're light waves or X-rays, and the whole list, they travel out at the speed of light. They really should be called the speed of electromagnetic waves. And they have all those wonderful properties we talked about in terms of they're made out of electric and magnetic fields. They're at right angles to each other. And if you know the strength of the electric field, you know the strength of the magnetic field. But for this problem, the feature that we need to understand is that this power, which is 4,000 watts, so 4 kilowatts, spreads out in a sphere. You know, in my drawing, I've done I guess I'd call this a two-dimensional drawing. And it's not an accurate representation, and so I guess I'm trying to get you to picture the surface of a sphere. Maybe I'll go back to the closest thing I have that's a sphere here in my room is this baseball here. So I got this baseball, and the surface area is where all that energy is spread out. And so that's what I'm trying to get you to see, this 3 dimensions. So when it says spread out over an area, we're talking about the area of a sphere. And the surface area of a sphere is 4 pi r squared. So this 4,000 watts of power is spread out over a, I'm going to come back here to the number, what was this, 8 kilometers. 8 kilometers from the transmitter. So this would be 8,000 meters. And so there's the first half of the problem. Maybe first third of the problem now that I think about it. But 4,000 divided by 4, also divided by pi, and also divided by 8,000 squared, comes out to be 4.97 times 10 to the negative 6 watts in 1 square meter. So by the time it gets to the receiving person, it is down a little bit. And I noticed a little delay. Not on my computer, but on my second one. So it must be a delay for you guys. Let's see. 1, 2, 3. Oh, no, it's just, yeah, it's just a
Seems to be in
they're
sync.
caught up. Pardon me?
Seems to be in sync.
Yeah. Yeah. Okay. I don't know if it was off for a moment and caught up or I was just dreaming. Okay. Okay. I think that's good. Okay, so now, sorry about that. I'm just checking out the camera here. Okay, so back to this problem here. All right, so we did the first part of it, which is the intensity. Now, the other thing to remember, and this was the part I was saying right at the very end of the lecture, I made the argument that the intensity would be the energy density times the speed they travel, which, since they're electromagnetic waves, they travel at the speed of light. And the energy density is 1/2 epsilon naught, the maximum electric field squared times C. And of course, that means, because we know the permittivity of free space, we know the speed of these waves, and we just figured out the intensity, we could get the strength of the electric field at this point. And the reason, of course, they're called electromagnetic waves is they have an electric and a magnetic component. All right, so I guess this would be 2 times the intensity divided by the permittivity of free space divided by the speed of light, and then the square root. So to do a calculation here, let me go ahead, grab my calculator and go 2 times the intensity. I should have cleared my calculator. 4.97 times 10 to the negative 6 divided by 8.85 times 10 to the negative 12 and divided by 3 times 10 to the 8th, and taking the square root of all of that, and I get this number of 0.0612. And it's an electric field, so this should be volts per meter, although it might be nice to check the units. The intensity was a watt per square meter. Epsilon naught. Ooh, that goes back a while. Let's see. We know that 1/4 pi epsilon naught. And then Q squared over R squared is the force. So I'll put, yeah, so it is, the units would be coulombs squared, and then over a Newton and a meter squared. Yeah, that sounds right. Make sure, Coulomb squared, I didn't get the upside down of this. Okay, that looks good. And then the unit for the velocity would be meters per second. All right, so let's see what I get here. So meters squared cancels off, and a watt, if I kind of simplify this, a watt is a joule per second. And then I've got the Newton and the second left over from here. And then I've got the coulombs squared per meter. Okay. Why don't I just cancel the seconds to make that easy? Still feel like, uh-oh, did I make a mistake here? But a volt is a joule per coulomb. So that would take care of one of them. Good. I think it's working out. Joule per one of the coulombs. Then I would still have a Newton per coulomb and a meter. So then if I multiplied the top by a meter and the bottom by a meter, this right here would be a Newton times a meter, which is a joule, and a joule per a coulomb is another volt. So that's volt squared over meters squared. Good. And now when I take these square roots, I get a volt per meter. Okay. So a lot of work. I don't know if that was very enlightening, but the units do work out. to be the correct unit for the electric field. And then finally, we can get to the last piece of this problem, and that is the connection between volt and electric field. I guess this is back to chapter 25. The definition was minus the integral of E dot dr for the electric field. And if the electric field doesn't change with space, and for our radio waves, at a particular moment in time, they are the same at that particular space. It changes with time, but I could then just say this would become E times its length, because you can pull out the E, and I guess this would be its absolute value, and then I just have the integral of dr, and that's its length here. And so now I can get the voltage or the magnitude of the voltage, and this would be the maximum magnitude if I put in the maximum field times its length. And so the field, as we said a moment ago, was this 0.0612, so 0.0612 volts per meter. And I'm multiplying it then by 0.65 of a meter. And so meter is going to cancel off, and I'll just have volts when this is all said and done. And so taking that number and multiplying it by 0.65 gives me a 0.0.
It is definitely getting laggy.
398. Yeah, getting laggy here?
Yeah.
Okay, I'll start writing 1, 2, 3. Yeah, it's
No, it's starting to catch up.
yeah, it seems to catch up. So when the lag is between somewhere out there in cyber world, it seems to catch up. When it's between my phone and my laptop, it needs to get reset. Okay, anyways, and that's step 3. So is to recognize this. So like I said, kind of 3 steps here. Get the intensity of it. And probably the main part is once you get the intensity, oh, no, it's lagging. I'm choppy there. Once we get the intensity, we can get then the electric field. And then once we get the electric field, we can come back to chapter 25 to get what is the voltage. And technically, this is the maximum voltage. And so it would be, sinusoidal. The voltage would be its amplitude, and it would change with time.
Okay. Yeah, thank you. I'm going to look at the part of that lecture again.
Yeah, okay. Yeah.
Yeah, that makes much more sense now.
Good. Good. All right, so then I'll jump off here to, let's see, I got enough room to put a little bit on here. In fact, when I grab those sheets of paper and set myself up for a couple pages. And go to the chat room. I think, Gina, you had one up there next. All right. So let me write it down. So yeah, the next question, Gina. Part 2, number 3. Thank you. Part 2, is that part 2 of the practice test, number 3?
Yes, please.
You out there, Gina?
Mm-hmm. Is my mic working?
Oh yeah, I can. You know what?
Oh,
I think
okay.
I turned mine way down.
Ah,
there's my problem.
Earlier, so cool.
I turned mine way down. Okay. No, that's because I was Zooming for my Thanksgiving, and we were all sitting next to each other. And anyways, there was all kinds of feedback. That's right. I forgot I turned down my.
Zoom giving?
Yeah, so my Zoom giving. My my parents and my in-laws. Okay, sorry about that, Gina. So I didn't quite hear you. Was this the practice test?
Yes, please.
Okay, so I'm going to write this down. Exam number 3. Problem number 3. The second part. And let's go here at 10:43. Okay, so what did I do with the practice test? Here it is. It's on this tab. Okay, and then the practice. Okay, so this is A, this is B. Okay, and then you said number 3. The toroid. The toroid consists of 500 turns, has a rectangular cross-section with dimensions as shown. A single rectangular loop, of radius 2 centimeters by 1 centimeter, and resistance of 5 ohms. It's traveling at a constant speed of 20 meters per second, okay, through the right cross-section of the toroid from the left to the right, okay. If the current in the toroid is 25 amps, what is the current, that is magnitude and direction, oh good, so we need to work with direction, when the loop is at the center? Okay, so the picture is a little challenging to draw. And it looks something like this. Here is the toroid cross-section 1, loops around. And so this will be cross-section 2. So that'll loop. Maybe that will loop. Okay. Hoping that's kind of looking like a half a something. Half of a toroid. Something. Okay. But the first half of this is to realize that in this picture, they show the current with these wires that come over the top and around. And it looks like over here, over the top and then down. Like arcs around, comes over the top and down. And it continues that. So that's probably enough to get the idea. And so we're going to have to go back to chapter 30 here and look at the magnetic field. And we've been doing magnetic fields in green. And so if I do this, the current going around in a counterclockwise direction, and I'll use right-hand rule number 2 here, okay? So by matching my fingers with the direction of the current here, I would be having my thumb pointing out of the paper or, towards the video screen. And so let me put a little circle with a dot, circle with a dot, circle with a dot. And I guess in the whole toroid, we would be coming around like this. And so the magnetic field would be going around inside of the toroid. And in this cross-sectional area would be coming up out of the paper towards you. Oh, in fact, my drawing could have been better because also from chapter 30, the equation for a toroid is this crazy thing. And what this says is R is measured from the center part of the donut hole, not from this edge or any place else. It's from the actual center of the donut hole. So what this says is in our problem, it looks like from the center of the donut hole to the inner radius is 5 centimeters. So if I put in a 5 centimeters right here, I would get the strength of this field, but it extends out. And so way out here, let's see if I can see in the picture, oh, is 10 centimeters. Okay, and again, to get the field way out here, I would put in the 10 centimeters into this equation. But the point I wanted to illustrate, if you don't remember it from chapter 30, is that the field inside of this toroid then is not uniform. It's strong near this inner radius and then gets weaker as you go out. And in this case, we double the distance. So that means the field would be half as strong out here at the outer radius than it was at their inner radius. So there's a variation in the field strength from strong to weak as we go from left to right. And that's what this problem says, that we move from left to right. Now to draw my little rectangle, maybe I'll do what would be a good color? How about a purple color here? Here is this rectangle in here. But the rectangle is now moving. And so far, I would say that everything I've done really is from chapter 30. It's from our last material. But now we finally get into chapter 31, which is Faraday's law. Faraday's law says if there is a change in flux, there will be an induced EMF. And I have that. That's why I needed to kind of remember what the field looked like. So if this was back here a little bit to my left, it would have a strong field going through it. And as it moves along, the field is getting weaker, and so we're getting less and less flux. So is there a change in flux? Yes. And because of that, there's going to be an EMF. And so that's the key to the problem here. Now, the question says, find the magnitude and the direction. I might as well do the direction first, since I'm set up perfect for that, because again, this rectangle, if something that looks like a little rectangle, about another little post-it note, I can kind of move it along here. What if I take my little post-its and actually let me make it kind of smaller. I'll do this and this. This will be my loop. It's still bigger than I really want here, but as this is moving along across here, we're going to have a lot of flux coming up towards the video camera, and then it's going to get less. Okay, and so we learned what we called Lenz's law, and we said Lenz's law, then the direction of the EMF or the direction of the current is in such a way that it opposes the change. So here's what this is saying in my mind. In my mind, I've got a lot of the magnetic field lines, these green dots. I got a lot of them coming out, a lot. And then as I move over to here, now there's less. So the current would be set up to make up for that change, which would be out. So if I take my right hand and point my thumb out, the current then would be pointing in a direction, or the current would be flowing, I should say, in a direction that would be counterclockwise. And so the current would be in this diagram, if I, whoops, I should do that in purple, should be flowing in a counterclockwise direction so that it makes flux coming out. So the secondary flux, because the primary flux is getting reduced down. So a lot of flux from the primary, a lot down to a little. And to make up for that, it would be flowing in this counterclockwise direction. So there's the part that says, okay, what is its direction? Now we can go on to the magnitude. And like I said, this is where the current set of chapters come into play. This is the Faraday's law that says the induced EMF, and technically it's a negative. That's mathematically how you would get the change in direction, but we keep doing it with the right-hand rule. So I'll just put magnitude and put a plus. And the flux is a magnetic flux, so I should put a little b there, especially now that we've done chapter 34, where we've learned that a change in electrical flux makes a magnetic field, whereas back in this chapter, we were trying to say that a change in a magnetic flux produces an electric field, which is our EMF. So we want to be careful now, whether we're talking about a change in electrical flux or magnetic flux. Both of them come into play. All right, but in this problem, it purely is a change in magnetic flux. As it moves across, it'll create a current there. Okay, so I suppose the one thing I know, and I didn't catch it, didn't say anything about multiple loops. Let me go back to the problem. Let's see, toroid consists of 500 turns. And I'm not talking about the 500 turns in the toroid. Yeah, there it is in the second sentence, a single rectangular loop. So this has just one loop in it. So the EMF in the rectangle, we would put a 1 for that one. Don't confuse it with this n, which would be 500. This is the number of turns in the toroid itself. So that's the 500 to make the magnetic field, but the number of turns in the secondary, that's this one here, that's that rectangle, would be a 1. And then it would be the derivative of the flux. And maybe I will write the flux of what it really means, and that is a dot product and an integral. Okay. Now, this dot product would then be what I like to do first, and it turns out to be 0 degrees because, again, the field, which is these greens, as we argued earlier, which is information from chapter 30, is pointing out of the paper. And of course, this rectangular plane is moving across, and so its normal vector, so I'll put A with an arrow, is pointing out. Those are in the same direction. So I would put cosine of 0 degrees there. And cosine of 0 degrees is 1. So I don't need to think much more about that one. Then the magnetic field is what we said earlier is mu naught Ni over 2 pi r. Okay. And then the dA, and I hope I made my drawing big enough that this will stand out, but we would have to then add up the field. And as we said earlier, the field is strong to weak, and so it's probably best to take this rectangle and cut it into vertical slices, because the field gets weaker as we go from left to right. And so the area of one of these little slices is what I'm thinking in my mind. I want to do this dA. And so if I call this little rectangle height h, then this area would be h times a thickness of dr, where each little slice right here has a width of dr and a height of h. So its height times its width is its area. And so then I can actually do this integral. And let's see, the mu naught is a constant. I can pull it in front of the integral. The number of turns in the toroid is a constant. The current is a constant. And of course, I should say again, a constant in space as well as time. But right now I'm just focusing on space. So I'll pull that out. The h, again, for the rectangle is a constant in space. The 2 pi is a constant in space. And of course, then the only thing that changes with space in the dr direction is r itself. Okay. And so this becomes, I'll leave all of these alone for a moment. This integral of dr over r. Actually, maybe I'll just do the integral because that's just the natural log of r. And I should put my limits here, but it's also, it's moving along. So why don't I do this? Why don't I say that at some moment in time, this edge is a distance r away. And that means the far edge would be r plus, and what were the dimensions they gave? Let me come back to the picture. Oh, so this is 2 centimeters. So let me write this as from the first edge r to the last edge, which is r plus 0.02. So this would be r to r plus 0.02. So this becomes, I'll leave all that alone for just a second, ln of r plus 0.02 minus ln of r, which I could write that as a quotient, and I often do, but I'm not going to do it this time because I see what's coming, is I got to take a derivative. And I do not want to do a quotient rule. And so I'm going to leave these alone. I'm not going to put those together. Okay. Now I can look at the time derivative. And so now we can say, okay, now what of these change with time? And all these here, which I had earlier said were constants, they were a constant not only in space, but they are also a constant in terms of time. And so I can pull all those in front of the time derivative. And so now I have a derivative with respect to time of that. Okay, and so that would be 1 over r plus 0.02. And then don't forget the chain rule. So the chain rule would be dr dt. And then more of the chain rule would be plus 0. So I don't need to write anything there. And then minus, and then the derivative of ln of r is 1 over r. And then the chain rule dr dt. And so I'll leave these constants alone for just a second. And if I come over here and notice that both of these have a dr dt, I can pull those in front. And I could even then kind of interpret, or what I like to call read the math and say, okay, what is this dr dt? And this dr dt is the rate at which its position r is changing. And so that's this r as it's moving along. And so that would be my v. All right, so now I think I'm ready to plug and chug into here. So permeability of free space is 2 pi times 10 to the negative 7. And by the way, there's a 2 pi down here, so I'll save some keystrokes and cancel that. The n, now this is the n of the toroid, not this n at the beginning, which was the number of turns in the rectangle, but it's this n, which is the strength of the magnetic field, which comes from the toroid, which is the 500. The current, they said, is 500 amps. The H, that goes back to this picture. This is the height of the rectangle, not the toroid, but the height of the rectangle. That's where the flux is. And so that was 1 centimeter. So 0.01. This is the speed of it. Let's see, moving at a constant speed of 20 meters per second. Let's see, the 2 pi I already took care of. And this would be 1 over, okay. Now, they say, and everyone got to be careful and think about the dimensions here. They say when it's at the middle. All right, well, coming back to this picture, let me just kind of copy it down below. If the distance to the inner radius is 5 and the outer radius is 10, then the middle would be 7.5 centimeters. And that means the edge of this rectangle would be at 6.5, and the other edge of the rectangle would be at 8.5. So the R, what I represented was this 6.5 centimeters. So knowing that, this would be the 6.5 plus 2. So that's the 8.5 centimeters. That's the far edge of the rectangle. And then minus the near edge. And I just noticed this is going to give me a negative sign. But remember, we did absolute value somewhere. So this technically is the absolute value of all of this. So I'm going to get a negative and ignore it. Or to put another way, I could have got the negative with the original negative and making it a positive. But going ahead now and grabbing my calculator, and I'll do this calculation first. 1 divided by 0.085 minus 1 divided by 0.065. That's my negative, as I said. It looks like it's about a 3.6. But ignoring that negative in my final answer, then, I have then times a 20 times a 0.01 times a 25 times a 500 times a 2 times 10 to the negative 7. And so this is the 0.00181 would be my EMF. So that's my voltage. And then now to finally finish the problem, we've got to go to chapter 27, which is Ohm's law, because the problem I think said current. It says, what is the current in the loop? So the current would be V divided by R. So 0.00181 volts divided by the resistance of 5 ohms. And so take that and divide by 5. And I get then a current of 3.62 times 10 to the minus 4. Let's see, that's amps. So if I write it in milliamps, 10 to the minus 3, that'd be 0.362 milliamps. So I hope I got, let's see, the same thing. Let me scroll down to the answers to B. And they got, yeah, they write it as microamp. So this is the same as 362 microamps. Good. Same thing. Nice. And let's see, volts. Yeah, they got a millivolt there. Point. Yeah, good. And that matches too. So everything matches. Hope that helps.
Cool. Thank you so much.
Mhm.
For a second, I thought that there would be no flux before I realized that the magnetic field wasn't uniform.
Yeah, that's right. And that's, I guess, very important. I got to keep emphasizing, it's half of this problem. Well, I don't know, maybe not half, but a big piece of a physics problem is, seeing that physical picture. It's not just, hey, let's plug this into this equation and solve, because if you don't know that first step, that the magnetic field changes throughout the toroid, then you're not going to see how there's a change, and you're not going to see how there's an EMF. But if you do see, and you got to see all of those, you have to see that the flux or the field changes within the toroid, therefore a moving rectangle has a change in a flux, and therefore there is an EMF, and now you can start doing the math. So I think you get that, but that's just the nature of any physics problem. Is the first half of it is the conceptual physics part, which is never so easy in itself, let alone then converting those ideas into mathematical equations.
So we were able to kind of ignore the top and the bottom of the loop. We just calculated the left side and the right side and used the fact that the tops and bottoms canceled.
I think it was solved in a different way where it's described.
Yeah, good point here. Notice that I might call it the long way, but I also might call it the more fundamental way. I actually just started with Faraday's law, did the flux, and I did this rectangle. I did the whole rectangle. I wouldn't use the phrase that you said, ignoring the top and the bottom. I would, I did the rectangle. But there is another approach you could do. And I noticed in the solution, and in fact, Don made it, he said, remember that we worked out in class that the EMF of a moving rod was VLV. So I think what you're getting at, Gina, is that solution took the rectangle then as 4 rods, and then said something along these lines. If you call this rod 1 and rod 2 and rod 3 and rod 4, then what you get in a voltage from beginning to end from number 2 is the same but opposite that you would get from number 4 beginning to end. And so if you add up the volts all the way around all 4 pieces, the voltage from number 2 and the voltage from number 4 would be equal but opposite, and therefore you can ignore them. And I think that's where you were going. So what Don did in this solution is he said, let's just take the voltage from number 1, and well, I'll even write it, plus the voltage from number 2, plus the voltage from number 3, plus the voltage from number 4, but argued that 2 and 4 would be equal and opposite and cancel off. And 1 and 3 would also be opposite but not equal because they are at a different field. And so you would get the EMF at number 1 minus the magnitude of the EMF from number 3. And so take the field, the length of it, and the velocity for number 1 and subtract off the field, the length, and the velocity for number 2. And then if you do that, and remember that the field is calculated from the toroid, you would get something that would look like this. You would get the field at the first rod minus the field at the second rod times its, now here's where I gotta be careful. The length then would be this distance, which I called h, so I'm gonna change my L to an h times the v. And the field would be this mu naught times n times I over 2 pi, and I'll call this R1. And this would be mu naught n I over 2 pi R2 HV. And if you look at the things that are the same and factor them out, you would have 1 over R1 plus 1 over R, I should call that a 3, it would look better. 3, 3, 3, 3, okay. And then I've got the mu naught, the n, the I over the 2 pi, which factor out of here. And then I've got the h and the v, and that is identical to what I got back here when I did the whole calculation as the change in flux, taking its derivative. I got this right here. See, the mu naught, the n, the I, the h, the v, the over the 2 pi, and then this would be 1 over the one of the radii, number 1, and then 1 number 3, although mine would be reversed from this. And so sure enough, if you put in your numbers, you're going to get that same voltage, 0.00181 volts. So I guessing here, Gina, that when you said I'm ignoring the top and bottom, you're talking about this solution. This solution, I probably used the wrong word there. I didn't ignore them. I justified that 2 and 4 would be equal and opposite, so I didn't have to mess with them. But I also pointed out that 1 and 3 could not be the same because they were in different fields, and therefore I can just use the result of the motion EMF and jump into the answer a little bit quicker than having to do this original derivation. But of course, this original derivation is how we got the BLV. So you can either memorize that and start there, or do it from fundamentals. And I guess I'm one to believe that in the fundamentals, start there, because I know what it's going to be easy to forget this in about 6 months from now. But hopefully this, which applies to every problem, is the thing that you try to learn long term and keep in your mind. Oh, my phone disconnected again. Hang on. Let me bring it back.
Can I ask a quick
E1
question?
and E3 will cancel, but it doesn't happen to be in the middle. Probably a little bit before the middle.
Now 1 and 3. Hang on here. Let me finish connecting the phone here. But 1 and 3 will always be at a different field strength, so they will never cancel, no matter whether they're in the middle or not. And then the 2 and 4 will again always cancel, whether they're in the middle or not, because the voltage is created over this length of the rod number 2, and rod number 4 is exactly the same scenario. It has, whether the field is strong here and goes to weak, or strong and goes to medium, at the same moment, the number 2 would be doing the same thing. So justifying that 2 and 4 cancel each other has nothing to do with the fact that it's in the middle. It's always going to cancel each other. You're always going to be going from a stronger field to some kind of lesser field. And if you're close to the beginning, it's not very much less, but if you're near the end, it's a lot less. But yeah, 1 and 2 always cancel. In the middle or not. The only place where the middle comes into play is near the end of it, where I actually have to then put in the value of R1 and R3. So this problem could have been just as easily have said some other spot. It has nothing to do with the middle. Same thing here. Nowhere in here did I do anything with the middle. This is just the position of the left edge of the rectangle. And then to actually do a calculation, I need to have some information to say, okay, well, where is it? And the left edge, is here. So this voltage, comes out to be this much when it's in the middle. But if it wasn't in the middle, I would still do the same calculation. I would just have a different R for the left edge.
Okay. Okay, thank you.
Sure. Sure, and then somebody else had a question on this, I think. They were asking.
Yeah. So I was just, after seeing you go through this,
Yeah.
it got me thinking about the first problem on this test, which is kind of similar. And
Okay.
I don't think I need you to go through the whole process, but I was just a little curious if you could explain why the current in problem 1 is the variable changing with respect to time, and what that current is specifically.
Oh, so is this are you talking about, let me come back to test A here, where it says you drop a metal ring horizontally?
No, for test B, when it's talking about the inductance for a toroid.
Oh, okay, yeah.
So that di dt, I'm assuming there's nothing moving in the magnetic field, so there's no positional variable changing with time. But is that
Right.
current changing? Is it the current in the toroid or the current induced by the EMF?
Oh, I guess it would be the current in the toroid. So I guess let me try to describe it in equations. The general principle is that an EMF is created when there's a change in flux. Okay. And the problem we just did, and I think what you're trying to say is, how is this problem different than the one we just did? In the problem we just did, the changing of the flux is not in the toroid itself, but is in another moving object.
Yeah.
I like to call that a secondary effect. Okay. So I would have an EMF in my secondary. Now, it is quite possible that the EMF we're talking about is not the EMF produced in a secondary object, but in the original object that is making the field. And if that's the case, then you can't have a change in flux because the object is actually moving, but you could have a change in flux because the current is moving. So what we like to say is, in the special case where the EMF is on itself, so we call this a self EMF, you could write this instead of the derivative of the flux as everything else and then how the current is changing. Because again, the only way you can get a change in flux on yourself is not by moving like we did in this problem, but by changing the currents that is actually in the wires themselves.
Okay.
And so I don't know if you would call this a simpler case. I do, because Faraday's law applies for any object, anytime there's a change in flux, whether it's a change in itself or whether it be a change in a second object.
Okay. Cool.
And so when you apply Faraday's law to itself, I'll say it again, the only way you can get a change in flux is if there's a change in current. So we like to write Faraday's law when it's a voltage on itself as all of this stuff grouped together, call it the inductance of it, and then how the current is changing in the toroid.
Okay.
So that's why in this problem, which, you know, you said don't bother to solve it. Okay, so I won't bother to solve it unless somebody else asks about it. But that's why in this problem, the focus is not on a second object like we just did. There's not a moving object, but the second object could have flux for a lot of reasons. It could be moving, it could be spinning, it could have current changing. I mean, there's a lot of reasons, or the toroid itself could be moving or spinning. So there's a lot of reasons of why the flux in the second one can change. So I'll say it again, the more general principle is this, but when you apply it to yourself, the only way you can get a change of flux on yourself, because you can't move relative to yourself, you can't rotate relative to yourself. All you can do, the only way to change the flux is by the current. And so we like to write everything else and then the change in current. And so if you go through the math on this, you'll see in number one, there is no secondary moving object, but you're looking at the flux, and maybe this was your question, it would be the flux over the whole cross-sectional rectangle. Whereas in this problem, I did the flux only within the secondary object, because I want to know the flux in that second object. Whereas if I were to actually solve problem number one, I would take the flux in the whole toroid because it's changing on itself.
Okay, I think that makes sense. So in the first one, you're describing the EMF created by the moving charges, and then in the second one, the toroid isn't really the focus, but it's the source of the magnetic field, which is creating the EMF in that moving object.
Yeah. Or maybe to put in this way is in the one I just did, the toroid is what I would call the primary. It's the thing that made the field. And then I was interested in how that changed in the secondary. But in the problem you're asking about, the primary is the same as the secondary. There's not two objects here. So I am interested in the field created by the toroid, because that's the primary. But I'm also interested in how it changes in the secondary, which is also the primary, which is also the toroid. So everything is the toroid. And it doesn't make any sense to talk about a primary or secondary for something like this. But I think it helps me anyways to think of it that way, because when you learn Faraday's law, you think about a primary, which makes the field, and then the change in flux in a second object, a secondary. But when you go to talk about on itself, that then means the primary and the secondary are the same object.
All right, cool. Thank you.
Mm-hmm. Cool. All right, let's see. We're back to our chat room here. All right, so that was a good one. I think we're on to oh no, that was 102. Okay. How about Jake? I believe there is a small error, in the solution of exam 3, number 3. I'd like to confirm. Can you please explain really quick why there is no current through the inductor at time equals to 0?
Yeah, that's me again. So I was asking two separate questions there. I should have split those up.
Okay. So let me start with your first question, though. Number 3, is that the one we just did?
I think it was number 3 of test A.
Okay.
And it was just a little unit error, but I just wanted to make sure in case because I didn't want to make a mistake like that on the exam. When it's solving for L, I think it has to do with converting the area, and it's multiplying by 1 over 100 centimeters to convert that to meters, that value. And I think it should be 1 over 100 centimeters squared, right?
Well, hang on. Okay, so let me jump down here. So he has, I think you're talking about, okay, so there's an L, and he's got the mu naught, the n squared, the A, and over L. Is that what we're talking about here?
Yeah, so I think it's just when he's converting the A to meters. I think that.
Oh, oh yeah. Okay, now I see where you're coming from, because he then writes this. He writes 4 pi times 10 to the negative 7. Okay. Then he writes the number of turns, 820. Good. Yeah, and then this area is 1 times 10 to the negative 4 centimeters squared. And then when you convert it, yeah, you should have 1 meter over 100 centimeter, and there should be a square right there.
Yeah, that's.
Oh, wait a minute though. Wait. But maybe he gets away from that because look at the denominator. He doesn't put it in meters, he puts it in centimeters.
But isn't that just the length?
Oh, right. So that's why he got rid of the square. See, oh yeah, this is kind of silly. See if this makes sense. So downstairs, he put 7 centimeters, and before he converts, so let me just cross this out. He notices that one of these centimeters down here would cancel with one of the centimeters up there.
Oh, okay.
And then he just converts once.
So, right, so he only needs to convert one of the centimeters. Now,
So
I think that's a little too
he's
confusing. So I would encourage you to do what you were thinking. Make sure that you squared it up here in the numerator, and then make sure you put this as 0.07 in the denominator.
Okay. All right. Thank you.
And you'll, but yeah, so there's not a mistake, but it is kind of weird.
Okay. Yeah, I think there was something like that on the last practice one that was tripping me up too. All right, that makes sense. Thank you.
Oh, and then what was your other part of that? Let's see. Let me come back here. You said, okay, was there an error? Okay, can you please explain really quickly why there is no current through the inductor at time equals to 0?
I mean, in a general case, when you have an inductor,
oh, in a general, okay.
You first flip that switch. Is it the back EMF that's preventing any current from flowing through that inductor?
Yeah. And let me say it a little differently though, then, because it's really based on this. The energy in the inductor is 1/2 Li squared. And if you then take the derivative with respect to time, that's called power. And you get this equation. You get a 1/2, you get an L, you get a 2, you get an I, and there's the magical key, di dt. I'll cancel the 2's, but the one I want to focus on is right here, di dt. This would say for the current to change instantaneously. So let's say you had a graph that says current versus time, and let's just say the current was, I'll just pick a number of 10 amps. Could it instantaneously reduce down to 5 amps or instantaneously jump up to 15? And this is saying to change instantaneously, that number would have to be infinity. And that's saying it takes an infinite amount of power. So the phrase we like to use is say, an inductor will never change its current instantaneously. It will build up to 15 amps, or it will decay away to 5 amps. It will never change instantly. So if you had a problem, and I think this is kind of what you're referring to, that has a switch, and then that switch is connected to maybe a resistor and an inductor in series, right before you close the switch, you know the current is 0. So if you made a plot of current versus time, you'd say, okay, the current is 0. Then when you close the switch, sure, it will build up to some maximum value, but immediately when you close it, it's got to be 0. And that means, as you said, there would be a back EMF created that would equal to the voltage on this battery. So when you first created it, this battery is trying to put current this way, and this inductor creates a back EMF of the same voltage, and that leaves the current at 0, at least for that moment. Now, so everything you said, I totally agree with. I just want you to be a little careful because you might have something that looks like this. Get a new piece of paper. If I had a battery, V, and a switch, this time I'll start with my switch closed. And it goes through a resistor, and then maybe I have an inductor and then a resistor. And I think this is one on the practice test. If you had that closed for a long period of time, the current would go through this first resistor, through the inductor, and then back to the battery. It would not go through here. And so this would establish a current of V divided by this R, call it R1. And nothing would be going through R2. And then if you open the switch, I'm going to come back to this statement. It's not a statement that says the current has to stay at 0. It's a statement that says the current has to be a continuous changing function. So when you open this switch, the current now will start to do this loop. And it will start to go through resistor number 2 and decay away once you've opened this. This battery is now out of the circuit, if you will. But a plot of the current would be to say, okay, before I open the switch, the current was a constant V over R1. And as soon as I open the switch, it is still at that same value. Now it decays away, and it would decay away through resistor number 2, but it's still gonna decay away.
And that's where you get your I naught times your E.
Yeah, right.
Quick question. In this diagram, and the camera froze, it looks like, but in this diagram with this, before this, when the switch is closed, why is it that that no current goes through the resistor 2? Why does it only go through the inductor?
Now the key to that phrase, I'll reconnect the phone here, but the key to that phrase is after a long period of time. Because watch this little loop here. Let me find my pen. Oh, here it is. If I just do this loop here, let me say A to B to C to D, and I do the Kirchhoff's loop rule. So let me look at loop A, B, C, D, back to A. From A to B, the voltage would be from an inductor, so that's minus L di dt. Then I'm trying to say this as the current, okay, if these were two resistors, you would have said the current comes out of here and it splits and it goes down this way, call it current 1, and then goes this way, call it current 2.
Right.
So I guess I would have called this current 1, then I would have been going against the current, so I would have called this R2 times current 2, and I would have got to 0. Okay? Now, after a long period of time, this is the key, the derivative would be 0. So I would have R2, I2 equals 0, or I2 equals 0. So after a long period of time, all the current is going through the inductor, 0 splits off and goes to that resistor.
Could that also be described by the current flowing to the path of least resistance?
Yeah. But I'll say yes, but let me add to that for a moment. Well, let's go back to something that looks like this. Let's say I have resistor R1, and then it gets right here and can go through 2 resistors. So let me just take out the inductor. I'll still call this R2. Let me just put this as R3. But if the current comes this way and splits, R2 and R3 are in parallel.
Mm-hmm.
So if we call this current 3 and we call this current 2, I would say current 3 plus resistor 3 has to equal current 2 times resistance 2. Let me write it as a ratio of currents and point out that in this case, you would not get all of the current going through resistor 3, even if resistor 3 is the lowest resistance. It splits. And so that phrase you say that the current wants to go the path of least resistance is
situational.
Yeah, I don't really like it because it almost says when you say, oh, electricity will go the path of least resistance, it almost sounds like you're saying, well, if resistor number 3 is less than number 2, then it will all go through number 3. And that's not what will happen. It will split. We call these current dividers. And how much it divides depends upon how much the resistance ratio there is. So in the case of an inductor where the resistance is 0, then what you would get, for this to match is you would have 0 resistance for resistor number 3, which means you would have 0 current for number 2. And that's the analogy to the inductor, that if you lower resistor number 3 all the way down to 0 resistance, that is the case, and only the case, where you'll get all the current going through the least resistance. So to say the current goes to the least resistance, like I said, is a little misleading. All the current goes through the resistor if it has 0 resistance, but that's the only time that occurs. Otherwise, it splits in some kind of ratio. I guess it would be a little bit like, take this analogy. If you're driving down the freeway, most of the cars are going to go on this big, wide freeway. If there's a side road, some cars will go down. But the side road has more resistance. So most of the current will go on the freeway. Most of the cars will go on the freeway. A few of them will go on the side road. But if all the cars decide to get on the freeway, it slows down and backs up. And as soon as that happens, that forces people off the freeway and onto the side road. And so the side road doesn't ever stop having cars. It always has a few cars in relationship to its resistance. And so the amount of ratio of the cars is the same as the amount of resistance. If there's a lot of stoplights on this little side road, then something like 99% of the cars go this way. On the other hand, if there's an accident on the freeway, then they immediately get off here and go the side road. And so they tend to more balance each other.
Okay.
Anyways, maybe I should go back to
Yeah.
Zach's. So that help? I mean, if you do this loop, it's only after a long period of time, and only because there's zero resistance would you say that all the current goes to this.
Okay, that does help.
So what is occurring that causes the resistance of the inductor to decrease? Like what is causing the magnetic field to dissipate over time?
No. Okay, yeah, good point. Number one, and I think you caught yourself on this one, the inductor doesn't have any resistance, but the inductor does have a reactance.
Yeah. Okay, yeah.
Okay. Now, here's where you kind of messed up on that statement. You said, what caused the magnetic field to dissipate? It did not. The change of the magnetic field dissipated.
Oh, okay. That's what's creating the EMF.
Yeah, the EMF is created by the change of the magnetic field. So once the current gets established and gets stable, there's a huge magnetic field. I mean, if I were to draw in green the magnetic field, it would be huge because of this current. But it is also stabilized at a constant current. And so it is no longer changing, and no longer changing means we no longer have a back EMF.
So that's only for a very, very extremely short period of time as that current just begins to flow through that you have that back EMF.
Yeah, now writing the equation, we say that the current is equal to the original current. And in this case, when you're opening it, it would be decreasing. In the case you asked earlier, it would be increasing. So I'll write it as an increase. But this equation for an increasing current, this time constant, was R over L. And I just want to be a little careful. You said a short period of time, and most of the time it is. But you could have a large resistance here. Well, let me not get into the numbers, but you could have a time constant such that this might take a couple of seconds. But usually, as you're pointing out, this all happens, within the time frame of a thousandth of a second.
Okay, so you're saying if you were to have a change in current or a buildup in current over a longer period of time, that would cause the EMF to last longer.
Right.
Okay.
Right. And so this important set of numbers really depend on how long this transition time is. And for most reasonable numbers, yeah, you're talking about just when you hook it up.
No, I've got another question, which is not specific to anything. It's just hypothetical again.
Yeah.
So if you have a circuit where, say, you have the inductor on one, and then in parallel to it, instead of another resistor, have it be a capacitor. Would that behave in much the same way, or would that be more because the capacitor becomes infinite resistance?
That I'll try to draw this picture. This becomes really complicated, and I'll point out we are not even going to attempt to solve this one. This is getting a little beyond what we did. Not to say we couldn't do it.
Yeah, I was just mainly like just out of straight curiosity and wanting to understand it.
Yeah.
If it's going to take like crazy amount of time, I don't want to distract from
Yep.
everyone else.
I'll answer it conceptually, not mathematically, but you could write these out in a system of equations, and you would have your 3 equations and 3 unknowns, and they would have derivatives and integrals in them, and we could solve this. So we are at a good position to solve something like this. We just haven't gone that far. This would be the next step, and this would be something we would do if this was a circuits class. And so I know some people in this class are in the circuits class. And this is the kind of thing they would, continue to study on. We're focused on things like electromagnetic waves and other things, but not just on all these different circuits we could do. But this would look something like this. As soon as you close this switch, as Jake was asking about, this would block it. This would create a back EMF, but this would let it go through. So this would go through like that. And then, of course, this would start to build up. And so you would, if this is current number 2, you might say current number 2 plotting, may start high and then start to go low. Whereas this here, if we call this current number 1 because of its inductor, it would start low and start to go high.
Which I remember seeing a graph of that simultaneously in one of the chapters.
And if that's all it did, then we could probably do that one and call it good. Here's where it gets really complicated, is after a long period of time where this current stabilizes, remember the voltage on this one is 0. So this here, once it built up a charge, would now be charged. And as this tries to drop down in voltage, this would then send its charge back through there. So the current would not only do this, but it would go negative and it would begin to oscillate. And ultimately, you would get on the capacitor, you would ultimately get 0 current. So it would look something like this. On the capacitor, it would go 0 current. It would pop up to some big value. Then it would oscillate and decay away to 0. Whereas in the inductor would start at 0, it would build up. Once it got too big, the capacitor would redo it and it would oscillate and then reach a steady state. And so there'd be these crazy oscillations that go on. Makes a nice set of differential equations. It's a great problem for your Math 220 class and to solve a system of differential equations, and especially solving this with Laplace transforms. But it's a very interesting dynamic play between the capacitor and the inductor, because yes, we can see what they're going to do long term, but they will transition to that in a very complex way.
Okay, thank you.
Yeah. All right, where are we here? Oh, hey, yeah, we're good. It's well past for time for a break. So, and there's no more questions. Why don't we take a break now, and we'll come back at 12:30. What do you guys think?
Sounds good.
All right. I will see you in, it's like 39 minutes then.
All right, cool.